this. Where is DNA found in a eukaryote? The nucleus. In a eukaryote, DNA is found in the nucleus. Where is DNA found in a prokaryote? The cytoplasm. Now again, if you're sitting there going, "Oh my God, I don't know this," worry. You should be worried. You're not putting enough effort in. This is not something you got to figure out. This is something you memorize. Name 3 organelles and their functions. You could have named any of them. Somebody give me an example. Mitochondria. What does the mitochondria do? Makes energy. I'm going to put makes ATP because that's the energy of the cell. Another organelle. Ribosome. So we should make sure we add a little notation here, not asked of you today, but remember this is membrane bound. In other words, there's a membrane around this mitochondria, not membrane bound. Which means what? No membrane. No membrane around this ribosome. What's another one? One last example. What? The nucleus stores genetic information is correct. Stores it, protects it, keeps it safe. Ribosome makes proteins. What is the path for protein production? You start in the nucleus. You were tested on this. You were given a question. You had to put them in order on the last test. Nucleus, message goes to the rough ER. Well, let me rephrase that. Nucleus. That has 2 choices. If it is staying in the cytoplasm, and what I mean by it, I mean the protein. Then it goes this way. If it is going to an organelle, or out of the cell, then it goes this way. If it's going to stay in the cytoplasm, it just goes to a ribosome floating in the cytoplasm. Why would I be upset that you can't do this? You did an activity in class. I gave you the answers. You created a flow chart. I gave you the flow chart in class, posted the video, and then tested you on a test. So at this point, you should know that this is important. Free floating in the cytoplasm. If it goes out into to an organelle or out of the cell, then it goes to the RER, the rough endoplasmic reticulum, where it's made. That's where the protein's made. The message, by the way, what gets sent to these things? A message. A message is sent. You know what? Let me zoom in. A message is sent to the ribosome from the nucleus. And what I mean by nucleus is DNA. So the DNA in the nucleus sends a message to either a ribosome in the cytoplasm, if it's staying in the cytoplasm, or a ribosome on the RER if it's leaving the cell, or it's going to be going into an organelle. So the RER it makes it. The SER is the next stop where it's modified and put into a vesicle. SER modified and put into a vesicle. Now from that vesicle, then from the SER it goes to the Golgi body, and I showed you the little proteins that transport the vesicles on the microtubules. And from the Golgi body, then it goes either to an organelle, if that's where it needs to go, or it leaves the cell. Which is why the Golgi body is called the post office of the cell. It's a ridiculous name, but I know I'm trying to connect to what you learned in middle school. And it's the place where it's the organelle that sorts everything and sends it to where it has to go. You have to label it. You have to put tags on it. In the SER, there's two functions, and that's to take and package the proteins to send to the Golgi body, and the other function is to detoxify. It has proteins and it can process things, so it gets rid of toxins. So when you go into the liver, which is one of the main functions of the liver is to get rid of any toxins that you ingest. So when you drink alcohol, the very first organ that deals with the poison, because alcohol is a poison, the first organ to deal with alcohol as a poison is your liver, which explains why alcoholics was one of the first things that goes for alcoholics. The liver. It's called cirrhosis. Why? Because they overwhelm their livers. If you look at a liver cell, it has a lot of SER. Why does it have a lot of smooth endoplasmic reticulum? Because the smooth endoplasmic reticulum detoxifies it. Anywho, it leaves the cell means it goes to leaves the cell, which means, by the way, it goes to the plasma membrane. All right, so that's the cell membrane, the outer membrane. So a lot of this has to do with membranes. To define a cell, to talk about a cell, you got to talk about a membrane. So let's move on. Let's talk. So here you have these bubbles, and they're not bubbles, they're spheres. They're spheres that are represent oil and water. Have you ever seen a vinaigrette? Do you know what a vinaigrette is? Yeah. So you put oil, olive oil, and vinegar, and sometimes some spices in water, and you mix it all up. And what you get is these oil bubbles, these little spheres of oil. Gentlemen in the back, we need to separate. I told you can't sit together, so one of you needs to move. How many people? How many gentlemen are sitting next to each other back there? You go ahead and move. You're up already. Go ahead and move. So these are spheres of oil suspended in water. They don't mix because oil and water don't mix. That's an essential idea. Biological membranes make fluid. They have to be fluid. They're dynamic. This is an essential idea. What does that mean, essential idea? It's vital. It's important. If you don't know it, you're not going to be able to understand 90% of the questions that are asked of you. So it's essential that you understand a biological membrane is not something that stays the same. It's constantly changing. That's what dynamic means. It's always changing. Fluid means it's moving. Yeah.
You have to write down the essential idea.
You don't. I would take notes. So whatever that means to you. I would, if I were you.
I wrote down.
Okay, I'm just saying, I would. If it says essential, you have it. Guys, you have all this. My goodness, I told you already. I printed it for you. If you put holes in it, it's right there. So there should be no question here. So when you look at the plasma membrane of a cell, again, what is plasma membrane? A plasma membrane is the membrane on the outside of the cell. It does these 6 things. The first thing it does is it holds the cell together. If it wasn't for this membrane, things would just float away. So this holds everything together. They're not really float. That's a little oversimplification because there's a cytoskeleton. Remember those tubules? They're all kind of stuck and attached to one another. But still, it wouldn't work as well. Control what goes in and out of the cell. We're going to talk about diffusion, osmosis, and transport next week. But the key is it controls what comes in and out of the cell. That's important. It kind of helps you become you. Like what makes you you? It makes those cells. Your cells are different from other people's cells. They're similar as well. We're all humans, so there's some similarity, but they're different as well. And the key is that one of the things that makes them different is stuff on the inside of your cell is different from the stuff that's on the inside of mine. In some extent, DNA is one of those things that's very different. So you protect if the cell membrane protects the cell. Why don't you move there? Why don't you move, get your stuff together, and sit up here. Sit right here. There's a space. I'll make a space right here for you. Come on. Come on, grab your things. Come here. Take a seat. I'll move everything for you. Here you go. Come on. There's a space. You can stop laughing. Thank you. Here's a space right here. Go ahead. Come on. Take that book bag off that table. Bring your things over here. Sit down. There's a chair, regular chair, somewhere in this room. Get it. Oh, there's a couple right up there. Sit right there. There you go. You can see the board and you're not distracted. Thank you. So allow the cell to recognize and be recognized. If I took my cells and I put them into your body would reject them. I can't take a piece of my liver and put them in your body. A regular chair. I would get a regular chair. It's going to be hard for you to write like that.
I'm not writing.
All right, get a chair, sit there.
Okay.
If you're not going to write, we will have a conference with a parent on why you're not taking notes.
Okay.
All right, very good. So I'm going to steal, Village. I stole some of your coffee, whoever it is that made the coffee. All right, I stole some. I left you some. Thank you. Yeah. Yeah. I'm sorry. You're going to need to take that to the office. So I'm going to write your pass right now. You're going to go to the office, and you're taking your phone, you're submitting it to Ms. Perez. Or you can explain to her why. Here you go. Let me take a pen out real quick.
Whoa, what you doing? You gotta stop that.
Sorry, guys, this is taking up some of our class time. I do apologize. If you're confused, it's likely that you're not paying attention. There really is no place of confusion. You either didn't do your work or you're not paying attention. I mean, that's where we're at this point.
I don't know if I should add some yesterday's notes.
Here you go. take this to the office. I took a picture. I will be emailing it to Miss or texting to Miss Prez. You want to take all your things? You may not be coming back. All right. That's up to Miss Prez, not to me.
I'm not going to come back.
Okay. Have a good one.
That's right.
So, what I would be doing if I were you is be taking Cornell notes and referencing my slides. I would take Cornell notes on my paper so I have room to add whatever it is I need to add. Yeah.
Well, I'm saying, like, should I add this on to yesterday's notes that I started?
That's a good question. Revise your notes. Yeah, you can do that. Or you can start another day's notes. Whatever, that's up to you.
Yesterday's notes, I already wrote.
You already wrote a lot of this stuff. That's fine. You don't have to write anything that's already up here on this page. If it's already on there, that would be kind of wasteful to rewrite it. But what you could do is highlight it. What you could do is circle it. If I say something or write something that's different than what's up there, you might want to add that. Does that make sense?
Yeah.
That really is what note-taking is all about. So yesterday, again, you had an opportunity to take notes on this. So let's move on. I know I don't want to read it all to you. I just want to start you off with putting things in perspective. So allow the cell to recognize and be recognized. So somebody asked, is that what rejection is? Yeah, that's right. If I give you a liver and you heard of organ rejection, that's because your body recognizes it's not your body. So what's your body going to do with something that doesn't belong to you? That's inside you. It's going to kick it out. It's going to kill it. Kidneys and hearts and eyes and, I mean, just about skin. Anything that's not you, that's in your body rejects it. It kills it. Yeah.
So, does your body just reject it normally, or do you get sick?
Great question. That's what rejection means, yes. It means you get sick. You get fever. You send white blood cells to the area to kill the cells. You kill those things. You destroy it. Yeah. Excellent question. Like one of my best friends his sister had a lung transplant. How did they survive? Well, I mean, what now? Same best friend. He has a lot. Well, we're focusing. I don't have that many friends. All right, so focusing. Hold. One question at a time, please. So what we're dealing with here is what happens is you get fever. You start to send blood to the area. The blood has white blood cells. Your white blood cells attack the cells of that stuff, that organ that got transplanted into you. And yes, you call that being sick. So fever, you pass out, you get sick really badly, and then the organ dies. And if the organ starts to break down in you, it'll kill you too. So they'll have to take it out. So it sucks all the way around. So that's what tissue rejection is. But how does it tell? It tells because of the outside of the membrane. I'm going to draw it for you in a minute. Yeah? Question, quickly, please. No, unfortunately, I don't. Yes?
How do the white blood cells attack?
How say what now?
How do the white blood cells attack?
That's a really great question. What happens is this white blood cells change their membrane. They surround it with their membrane. I showed you that. A cell eating another cell. That's what white blood cells do. They surround the other cell. They engulf it. They use lysosomes to break it down. They hydrolyze all the polymers, and they break it down into subcomponents of the molecule. So really, they utterly destroy it. Yeah. I see what you're saying. What would be an example of something that doesn't belong? If you got hurt, could you close those computers, please?
It's like coffee.
Yeah, because we have coffee brewing. So trying to focus. So if you get sick, you get in a car accident, you go to the hospital, you're A blood type, and they give you B blood type, what happens to you? Why? Why your body rejects it, and you get sick, and the cells break down, and you have a bad immune reaction, and you die. How did your body know that blood wasn't A, it was B? Because of the outside of the cell. The outside of the cell has markers. Shh, we're focusing. I'm not playing games with you guys. We got things to do. The outside of the cell has markers. Allow the cell to bind to other cells and molecules. Now, you ever wonder, you look at your skin and wonder, if you're made of all these trillions of cells, how do they all hold together? Are they glued together? Is there glue? Like, how do they hold together? Well, these membranes, they link. There's little proteins that link them together, almost weld them together. These proteins connect one cell to the other. Can we not get out of our chair, please? What? Oh, you're getting something? Okay, well, hurry up. Yeah. The cells are held together by the membranes. They bind to each other. The site of biochemical reactions and enzyme reactions happens on the outside, along the membrane. So there's a lot of stuff happening on this membrane, a lot. So if you take oil, like I said, and you put it in water, what you get are these bubbles, and they have these properties, and they're not really bubbles. This distracted behavior has to stop. Have I not proven this is an issue? One at a time, go and get what you got to get. Take a seat, finish the notes, and let's move on. So oil droplets, they come together. You take that vinaigrette out of the refrigerator, and most of the time you're going to see the olive oil on top. You'll see the water and vinegar at the bottom. So before you pour it on your salad, what are you going to do? Shake it, mix it up really well. And then you get these little bubbles, little droplets. They're really droplets, not bubbles, of oil that kind of float around. That's because these nonpolar materials dissolve nonpolar materials. Like dissolves like. So oil dissolves oil, and polar materials dissolve polar materials. So they separate. Now, as we look at this is actually the same phospholipid I drew on the board in the notes 2 days ago. They just have it with what's called a space filling model. Imagine if you took atoms that are of the right relative size, a plastic model of an atom, and then stuck them together. So, could you take that thing that looks like a xylophone and hang it up? Hold it up. Right there, that thing that looks like a xylophone. Hold it up. Quickly. This is, bring it here.
It broke.
It didn't break, it fell off. They come up. Bring it here.
It broke it.
They come up. Oh my God. You guys are pushing me today. All right, so what we have here is a model. And no, they didn't break. They act like hairpins. You can. Oh. They did not break. They act as. The problem is that they are not meant. They're not permanently affixed. Can we stop distracting each other? Can we stop, please, all this nonsense? So these go together in a model. This is a plastic model of DNA. And this shows you here, a C goes with G, and A. If you don't know what I'm saying, then you got problems. You got problems that are bigger than this class. You better come after school or go see a tutor, because you're going to be behind. I'm sorry. But if you don't know that C goes with G and A goes with T by now, base pairing models of DNA, then you got problems. So this is a model, and what the model is showing you is how they interact, and then if you align them correctly, they would form a double helix. All right? So this is just a model of DNA, and you'd have to fool around with it and bend it in a certain way. My God, stop saying that, man. I don't know what else to say. So that's what this is. We have other models up there. You're going to build them yourselves next week. But for a phospholipid, for a membrane here, these are balls. The balls represent atoms, and you put them together into a molecule. You know, you're all being recorded, right? This is being recorded. I'm publishing this the way it is. And your parents have told me we listen to this. I'm glad. I said, I'm glad because I want you to see and hear what goes on in this classroom. So when they hear the giggling and the talking and disruptive behavior and they read the referral that I'm going to write, they're going to know it's you, not me. So stop behaving this way. You're going to end up in trouble. And I'm not changing this. I'm not editing this out. I'm not. I'm sure your parents will recognize your voices. So when we're talking about space-filling models here, they're connected in a way to take this drawing here, but show you how it fits, how they would all fit together. So see, this is the head, the phospholipid head. And then this is a saturated fatty acid. This is an unsaturated fatty acid. They're hydrophobic tails. Hydrophilic head, hydrophobic tails. If we took and drew them out as a schematic, then you would see a hydrophilic head and two hydrophobic tails. And why is it hydrophobic? Because they're fats. Fats don't mix. Oil does not mix with water. That's why those previous pictures were the way they were. So you have, now this is not oil and it's not water. It just has a water-loving side and a water-hating side. Water-hating, water-loving. Water-hating, water-loving. So this outside is water, extracellular. Extracellular means outside the cell. The lumen of the cell means inside the cell. So both outside and inside have water. The parts that love water point towards the water. The parts that hate water point away from the water. That should make sense to everybody. Yeah.
Is there any way to mix water and oil?
Yeah, we do it all the time. We call them emulsifiers. So what we do is, this is the way you mix oil and water. In fact, let me get to that. That's the next slide anyways. By the way, a molecule that's both polar and nonpolar, something you should maybe stress. It's in your notes that you're supposed to take yesterday. Make sure you highlight it, underline it. It's a molecule it's called amphipathic. Amphipathic. It's written, you have it already. Again, for the 5th time, give me the Rubik's Cube. It's in your notes. It's in your notes. I printed it for you. So amphipathic means it has both properties of both polar and nonpolar properties. Now, the question, how can we get fats to mix with water? This is your question, which is an excellent question. I don't know how long, I don't know the history exactly, but I would say for thousands of years we've been making this stuff called soap. And soap is an amphipathic molecule. It has both water-loving and water-hating properties. Now, how do we do that? How did we make this thing called soap? We took fat. You can take any oil, by the way. You can take olive oil. So you see soap made of olive oil, you'll see that they use olive oil. You can use animal fat. You can use lard. You can use coconut oil. So any fat. And you take it in a big vat, a big pot, and you add something called lye. Lye is a mineral that's found in the earth that is very basic, like bleach. And you mix the oil, this lye, with the fat, and what you get is one side of the molecule is going to be water-loving, the other side is going to be water-hating. And when you mix those two like that in water, what happens is the part that hates water, the fat, is going to be inside this little sphere. It's a ball. And on the outside, you get the part of the sphere that loves water, of the molecule that loves water. Now, this is three-dimensional. So when you look at this, you need to consider that these things are not they're spheres. They're three-dimensional spheres. And what we do in this drawing, what we're doing is we're cutting this in half, and then we're turning it so that you can look at it. And so what you see is you see the green outside that loves water, and then inside you have the yellow hydrophobic tails of the phospholipids. In this case, phospholipids, but in any molecule, they have the water, the hating part inside. That's taking, but see, on the outside, the part that's facing the water, it's all water loving. Does that make sense? I hope that makes sense. So when you're looking at this drawing, this is a drawing that's been cut in half. It's a sphere, a ball, that you cut in half, and you're looking at the side of it. And so what you're looking at is that in the inside of this ball, it holds fat. All the water hating stuff is there. All the water loving stuff's on the outside. So that's what happens naturally. It organizes themselves in this way. And so you use this kind of technology used all the time. When you're at a picnic and you get an oil stain on your favorite shirt. That sucks. You can't let it dry, so you quickly go take it and put it in the washing machine. Do you just use water? Why wouldn't you use water to get an oil stain out? Because it won't work, because oil and water don't mix. But if you take soap or detergent that has these little micelles in it, and there's this globule of fat sitting on your shirt, then as these micelles, and there's millions of them, there's millions of micelles out there in that soapy water, in that washing machine. Say what now? I can't hear you. So as these little micelles come along and touch the lipid, the lipid gets trapped. The fat gets trapped inside the micelle. Now the micelle is floating around with the fat in the water. Now, right before the spin cycle of your washing machine, what happens to that?
It disappeared.
It doesn't disappear. What happened? It drains. So all these leave.
That's not what he said.
I don't care. I can't. With your silliness, I don't care. And the silliness can keep going. Again, I'm going to make sure that our next parent-teacher conference, your parents, especially your parents in this group, because this is the group that we're talking about. I don't want to mention any names, but let them listen to this. Let them listen to the struggles that certain students, not many, it's actually a relatively few number of students, cannot get their lives together. I don't know why. Not everything's a joke. So these lipids, these micelles, take the fat out of your clothes. That's how they clean your clothes. What about stuff now that's for non-polar materials, right? That's for fats and oils. What about polar materials? What about salt and other things that are polar?
So you said the
That's right, just the water. The water dissolves. Yeah. Say what now? So the micelles in the detergent or the soap.
So the micelles in the soap, right?
The soap, that's right. That's what good soap is. Strong soap is they have these micelles going on, and they just take this, all leaves with the right before the spin cycle, all these micelles leave with the oil, with the non-polar material that's on your clothes.
What's in the micelle that makes it, that could make the stain go away? What's in it?
I literally just explained to you that this is, oh, you weren't in here, I'm sorry. Could you watch the video in a little bit? And when I post it, it's a really good question. I'm sorry you weren't here when I explained it. Yes.
So you know how ducks, you also have to be out on the ducks and use Dawn, it have
Dawn, Dawn has a lot of micelles. That's right. You know on the Dawn commercials, you know that they have those ducks that got stuck in oil and they use Dawn soap to get the oil off them.
Yeah.
They use that Dawn because Dawn has a lot of these micelles in it. It's a good detergent. By the way, a lot of those ducks and birds ended up dying anyways because the oil got inside them and they couldn't survive. So a lot of them died, not all of them, but just so you know.
Ducks naturally have oil on
That's a good question. She asked a really great question. Really, these are all very good questions. What about ducks that have oil? They have oils and wax. Actually, the oil that they have is more of a wax. So if you ever look at a bird feather, it has a waxy film. And the difference between wax and oil is that wax is solid at room temperature, and it covers and protects. And so these wax coverings, water hits them, it doesn't get absorbed. It falls right off. And the reason is because it's nonpolar and the water's polar and they don't mix very well. They will dissolve it, but it takes a long time and a lot of water. So the duck doesn't ever really get wet. So that's a good thing. Now the difference here is that duck's wax and the fat, oil in your hair, for instance, or oil on your skin, lotion, for instance, is not an amphipathic molecule. It doesn't have a hydrophilic and hydrophobic. That's just the hydrophobic. That's just the fat. No head.
How do you spell amphipathic?
All right, it's on your note. It's in your notes for the 6th time. It's in your notes, and I've said it in class. Yes.
So how do frogs get water?
I don't know. We're moving on. All right. And I understand the reference. Not funny. We're not going to talk about it on the video, but we will talk about it after class. All right. So when we're talking about micelles and liposomes are an interesting artifact that occurs as well. This is when you have a micelle when they all form a ball of fat surrounded by the outside by the hydrophilic ends. But if instead of having one ball, you have 2 layers of fats. If this forms, then what happens is you get a hydrophobic, meaning water hating, all right, hydrophobic center between the 2 layers. Then you have a hydrophilic part. You have a hydrophilic. Just keep it up. It's okay. What I'm gonna do is I think I'm gonna go ahead and start the lab. Then I'm gonna call you in the back room one at a time. We're gonna call your parents. And if they want, if they want to say they want to listen to who's doing what, who's saying what I'll do is I'll post this. While I'm calling your parents, I'm gonna go ahead and post this on YouTube, and then when it's posted, your parents want to say, well, she says this, she says that, he says this, he says that. I'll say, why don't you listen to this? Listen to this. Let's see where we go from here. Hydrophilic ends are on the outside, but also on the inside. See, there's water here, and there's water outside. There's water inside and outside. So the parts that love water are going to point to the water. The parts that hate water are going to be in this section right here, in this filler section. Now this is going to be very important for you to understand. No, this is very important for you to understand.
Wait, so
Go ahead.
so the part that's inside of it hates water, right?
That's right. When you have a double membrane, see how there's two layers, not double membrane, but 2 layers of phospholipids? Mm-hmm. We call that, the name for that, when you have 2 layers, is a bilayer, correct?
What is that circle thing you call? What is the name of it?
This is called a liposome. So it's right there in your notes. It's called a liposome. It's a kind of vesicle. It's a kind of simple vesicle that allows you to carry stuff that you might not want roaming around in your blood, but it might carry anything that's positively or negatively charged. It could carry things that are polar in here and things that are non-polar in here. So these are very, very useful little things. We can actually make these in a laboratory. We have a liposome machine so that we can send materials to specific tissues if we'd like.
A what machine?
It's a liposome machine, makes liposomes. And we can add whatever we want inside that's polar. We can add whatever we want in the membrane that's non-polar. So it's a very useful tool. Yes.
So what does shampoo do?
Same thing. Moving on, same thing. So a lipid bilayer, this is a bilayer sheet, and what you see here is that there's two layers. Please pay attention. You have a hydrophilic head. I'm coloring in blue here. That's all. These are from the side. You can see that they're blue, and from the top, you can see each of these would also be blue. In this case, in this color code, you can use any color. They're not actually blue. I'm just using blue for hydrophilic, water loving. And you can see on the other side, you also have these hydrophilic heads. There's a reason I'm coloring them in. So I hope you're paying attention. You see all these are going to be hydrophilic. They're all going to love water because over here is water, and inside the cell there's water, and outside the cell there's water. The only place where water's not going to be welcome is here, the part that hates water, the hydrophobic tails. All right, so this is an important idea. You're going to use this today to solve your problems. You're going to have a multitude of problems to solve today. We're going to talk about this next week, this idea of active and passive transport. We'll be talking about this next week. I don't want to focus on this today, but there are ways for us to get things through the cell. So that's a question then. So if you have these two layers, let's take a look at them for a second. You have these two layers of phospholipids. You have, let me use blue. You have a layer, a bunch of heads here, and a bunch of heads here. And in between, you have these tails.
How would that work with the water?
In here is all fat inside here. So all this is non-polar. And I'm doing a very simple drawing. This is called a schematic. It's a model. This doesn't really look like DNA, right? This does not look like DNA. It represents DNA. So this doesn't really look like a cell, but it represents the components of the cell that I'm talking about. That's what we call a model, M-O-D-E-L. It sounds funny, but a lot of people don't really understand what a model is. So you really should make sure you understand that. So this is a model of a cell. And so inside you have this hydrophobic part, and then it has those hydrophilic heads. And of course, inside here you have water, and outside you have water. Now if this was and remember, I'm going to say it again, and I want to make sure you understand that this is actually a cutout. If you took a ball made of, it's really important you understand, if you take this ball made of these molecules and you cut it, right, and you cut it, then you look on the inside, that's what you see here, okay? So inside the sphere.
So basically it's like a big circle.
It's a big sphere, like a basketball or baseball, but you're cutting it in half, and you're cutting it in half, and that's what this drawing is. Okay, it's a cut. It's huh?
Yeah, where are you cutting that half to get that?
Literally cutting the cell in half, and I'm turning it. Imagine you cut an orange in half. I cut an orange in half, and then I show you the flat side. That's what you're looking at here.
That little thing you made.
That's a cell. This thing's a cell that I cut in half. So this is a cell. On the outside, I see how I drew a blue line? That's because the outside is all covered in blue. The inside, there's also a blue line. And then inside, you have, hold on a second. So a lipid is just a fat. So that's these yellow fats. The saturated and unsaturated fatty acids are lipids. Each of these phospholipids have a phosphorus. Let me do it in blue.
Every single fat is hydrophobic.
Yes. Yes. All fats are hydrophobic. Yes. 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 Yes.
That's not the question I'm asking.
No, he asked it. That's what he asked, not you. So, what is the difference? You asked, what's the difference between a lipid, right? A liposome.
And a micelle.
Lipid and micelle. A micelle has no inner see how this has the inner space? So it's all nonpolar inside. A liposome has a nonpolar interior, but then it has a little polar side inside, a space. So a liposome is a lot more like a cell, because that's what a cell is. A cell has a bilayer, right? That has the lipid side internally. Then there's a hydrophilic outside and inside. Has everybody got that?
Yeah.
All right.
Don't have a cavity, my cells do.
Opposite. My cells don't have a cavity. Liposomes do. Again, look at the drawings you have. I have handed out to you. No, I understand, but I had it out to you. You have it right there on the table. Did you grab one? It's also posted in Schoology. Okay, so here's a question. What if we were all in a box? This room had no windows. If we were in this room, like we're in a cave-in, let's say. But let's say somebody bricked up all the windows and doors. And we wake up, and now we're in this box. It's all right. We need food and water, right? And we need to get rid of our poo and pee, right? How do we get things in and out of this room? What do you need? No, okay, good guesses, but listen to this kind of thinking requires you to listen first. So listen and use your imagination. No, I need you to listen and use your imagination. If you were in a box, a ceiling, a floor, four walls around us, no windows, no doors, what do you need to get stuff in and out of this room?
A door.
A door.
You need to go. I'm in the middle of the class. You need a door.
My teacher sent me here though.
Oh, for what?
Because you have our power strips from when y'all tested.
No, I don't. Who's teacher?
Must be.
I got one power strip. That's hers. One of hers. In the back on the table. Okay, I'm in class, but I got to get going. It's not easy with disruptions. It's too much. Gosh, she getting mad at me when she's coming in this room asking me stuff. All right, so anyways, what we have here. Good Jesus, God, give me strength. So what we have here is, if we're gonna get stuff in and out of this cell, we need doors, right?
Yeah.
Yes.
Yeah.
So that if this was a closed system, if it didn't have any nothing would get in and out of your cell. You have to get stuff in and out of your cell, correct? Okay, so please consider this. So what we do is we put these proteins in our membranes. One type of protein that we would put in our membranes for it to function well is a protein called the channel protein. So this part is hydrophilic because it's in the water, right? This part's in the water here. It's hydrophilic. Right now you're writing, drawing, listening, and thinking. That's what you're doing right now. So then you have this protein here. So it's a protein, but it's hydrophilic. How do I know it's hydrophilic? Because it's sticking out of the cell and it's sticking into the cell, and there's water there, so it has to be hydrophilic. All the blue is hydrophilic. That's what color coding we're using here. It loves water. So that makes sense. What does not make sense, however, is that This hydrophilic part's touching this yellow part. Do you see that? Does not make sense. So what happens is this protein has a part of it that's yellow. Has a part of it that's yellow. In other words, there's a part of it. I'm gonna draw it. I'm gonna outline it in green here. I'm gonna put a little. You know what? Let me just use black. There's this protein. It's a protein that's embedded in the membrane that has a part that's yellow. I'm just drawing a little black here. That yellow part is hydrophobic. It doesn't like water. That's the part. Then part of the protein loves water. So the part of the protein that loves water bends and folds and points to the water area. The part of the protein that hates water, it bends and folds and points towards the hydrophobic area. So then you can have a protein that, like this one that I'm drawing here, that is embedded in a membrane, stuck in a membrane, that allows things to go in and out of the cell. So this is the cell's doors. Things are going in and out of the cell through this channel. It's called a channel protein.
So that protein going in and out the cell, right?
It's a channel protein is a protein that goes across the membrane, so it has a hydrophobic area, hydrophilic area, and it goes across the cell. Now, I'm drawing it two-dimensionally, but if we were going to look down at the cell, what you would see is a bunch of these heads, these hydrophilic heads, right? So these big blue heads. And then you would see a hole in the center. You'd see a hole in the center here. So this is an opening. It's a hole in the membrane that allows things to go in and out. But how do you create a hole that you can control? Is you embed a protein. It's a protein. I do it this way to make sure you understand that this is cut in half, like an orange. I cut the orange in half. I'm looking at the flat side of the orange. So let's remember perspective. So that's one kind of protein. That's one way to get things in and out of the cell. There are other kinds of proteins that have gates that you control what comes in and out. So you have another protein, looks very similar, has a hydrophilic part that sticks out, hydrophilic part sticks out, hydrophilic part that sticks out. It has the hydrophobic part of the protein is a hydrophilic part of the protein is still it's in this channel in this opening here, and then it has a part of it. You know what? Why don't I just do it in like orange or something? I don't know. There you go. So you got this part. I'm drawing it in orange so that you why didn't it? Wow. So I'm drawing it in orange so you see that it's part of this protein. It's hydrophobic. It's interacting with the hydrophobic part of the protein of the lipid bilayer, the lipids, right? It's still part of the protein. It's just in the membrane. The hydrophilic parts are sticking out and going through the membrane, just like the channel protein. The difference is that it has a gate. What do gates do? They can keep stuff out, but what is one thing that gates do? They open and close. So these are called gated channels. There's still channels, there's still holes in the membrane, but they're gated. There's channel proteins, there's gated channels. Now, we talked about rejection, that on the cell surface, there has to be something that helps identify you. Like if you're O blood group, you have something on the surface. You're A blood group, you have something on the surface. And B blood group, you have something on the surface. So let's say you have A blood group. So So you have a cell surface protein that sticks on the outside of the cell. And all on the outside, you have these spikes. And you've seen the COVID spikes on the news. COVID has spikes as well. You have these little protein spikes that stick out.
The spikes mean they're bacteria or something?
No, they're just proteins that you made. You put them in there. So they stick out. So they have to be hydrophilic. They have to love water because they're sticking out. All right. So they're sitting there like this. Now, if they're sticking out like this,
What are they called again?
I'm going to tell you in a second. Cell surface proteins. So these are called cell surface proteins. They're used to identify. They are ID proteins. They're used to identify you as you. So if you have A blood type, you have triangles on the outside of your cell as a simple example. If you're a B protein, you have circles on the outside of your cell. I'm just giving you simple examples. They're not that simple. If you look at the drawings in the notes that I printed for you, they're very complicated shapes. So they're on the outside of the cell, and they identify you as you. They're cell surface proteins. Now, for them to sit on the surface, that's great, but they need to be connected to the membrane. So what they have is these little, again, I'm going to use orange. They have these little orange parts that are hydrophobic that sit here, and they're still connected to the membrane, the protein. They're part of the protein, but they just bend so that they can stick inside the internal part of the membrane so that they can stay in the membrane. So it's like a tab. Think of it like an anchor. In fact, these are called anchored proteins. Another word for these are anchored. So they're anchored in the membrane. They have a little part that sticks in the hydrophobic part of the cell membrane, but a lot of it sticks out, and it allows the cells to communicate to identify you as you. Yes.
Can I take my mama real quick, please?
No, please. We're focusing on getting this done. Thank you.
I need to see if I can pick up.
I don't know what to say to you, dear. All right, so
We still need to analyze it.
the next part, another type of protein that you can see, you have to consider a different function. Let's say we're back in our box in the classroom. 4 walls, a ceiling, and a floor. So there's no way, we're all bricked in. And outside the room is a phone. Outside the room
Is it what?
is a phone.
A
A
phone?
phone.
A phone, oh.
Like,
He said phone. Phone.
A phone. A phone. A phone.
No one has a phone in here?
Please stop talking and listen to what I'm saying. Outside the room, you have a phone. And someone calls. Someone signals, right? Someone signals and they call. What good is it?
No, can't get to the phone.
Can't get to the message, right? The message is outside. So how do we get the message inside? How does this work? How does this phone work? How do we get a message from outside this room to this phone here? How do we do that? We have a wire that goes through the wall. A wire crosses the wall. Does that make sense?
Yeah.
We drill a hole in the wall and we put a wire through it. And something happens out on that side of the wall, it rings on this side of the wall. Does that make sense? That's the signal. So there's the signal is when you receive the message. But then the signal has to be transmitted. So we talked about insulin in this classroom. So you have these proteins that sit on the cell surface, more cell surface proteins. And they have specific shapes. And these are called, when we talked about feedback mechanisms, we talked about these things called receptors. So something's going to receive the signal. The shape, you don't have to draw it exactly like this. It just, the point is there's some kind of shape. And the signal that's sent from another part of your body fits into this receiver. So if this were insulin, it would look like something like this. Just as an example, the two pieces would fit. And as this molecule called a hormone, you know this word hormone, we've talked about in the past. As you have this hormone that fits into you have this hormone that fits into the receptor. This molecule here is a receptor. So this is the signal, also known as a hormone.
Wait, so the receptor receives the signal and that's the signal.
The receptor receives the signal. That's good. That's part of it. But how do we get the signal inside the cell? What do we have to have? You have to have a transmitter. You have to have a cable. Something is going to transmit the signal across the membrane, right? So you have to have something that gets the signal from the out. Okay, we got the signal. The cell received the signal. But how do we get the signal in the cell? You have to have something that crosses the membrane. And of course, it has to be, that part that crosses the membrane has to be what? Hydrophobic. But the part that sticks on the outside and the part that sticks on the inside has to be what? Hydrophilic. So there's going to be a part that sticks on the outside. It does something. Who knows what it does? It continues to send the signal forward. So they're connected. These two things are connected.
Ain't the one thing the tab everything?
Yeah, it's like the tab anchor thing. That's right. Except this time it's not just holding it to the membrane, right? It's not just anchoring it to the membrane. It's signaling. It's helping get the signal from outside to inside. All right? Does that make sense? We get the message from outside to inside by making sure we have a protein that can cross the whole membrane. So this side receives the signal. This time does something. This binds. This does something. You don't have to know what it does. It's just the idea of how it works is the only thing you have to consider. All right? This is what we call a signal receptor or hormone receptor. This is the signal transducer. So it changes it allows the signal to go from the outside to the inside. This here is this is a cell surface protein. It IDs the cell as you, helps identify you as being part of you. They sit on this. They need anchors, right? So they need to be embedded in the lipid part. This is a gated channel, so it opens, allows things in and out. And this is a channel protein, allows things in and out in a different way. This has a gate that can open and close. This one is just a channel, just allows things to go in and out. Yeah.
I have a question. I had read in chapter 7 about this thing called selective permeability.
That's right. Good.
Is that
Excellent. Oh my God. That is so beautiful. Thank you for saving my sanity today. So you have this thing called selective permeability, and that's it. This is it. This is how cells are able to choose what they allow in and out. They choose what proteins they want to put in the membrane. If you want to let sugar in, you put the sugar channels in. You want to let salt in, you open the gated channel. You want to, what you let in, you control by what doors and windows you put in the membrane. It's called selective permeability. It allows some things in and other things not. Yes?
That's what I've been missing the books and everything
selective permeability and then what's the cell, what the cell wall does too. Remember how it's permeable, the other one.
Which one? The selective permeability and what now?
There's another one that also chooses.
Both, they probably mean the same thing. You'll have to look it up and tell me which one and come and see me or talk to maybe next class session, ask that question. But selective permeability or semi-permeable is another thing they say. All pretty much means the same thing. You allow certain things in and other things not. This membrane will not allow ions through. You will not get any large polar molecules or charged particles through this lipid layer unless you have a channel. If your cell wants to let them in, they'll open a channel. If they don't want to let them in, they'll close the channel or get rid of it. Does that make sense? So they select, they choose.
Wait, how does like the receptor and the signal, how does it know what it is? And how does it know if it's a sugar?
Okay, so with the idea of insulin, insulin is a protein, it's not a sugar. And it has a specific shape. The shape matches the receptor. When they bind, it changes this whole protein twists and turns. And when it twists and turns, it does something. It continues a signal inside that tells the cell, hey, put some channels that let sugar in the membrane. And then the sugar leaves the blood and goes into the cell. And it happens all over your body. Trillions of cells all over your body start, boom, message sent, channels in, let sugar out. So your blood sugar drops quickly. Within a half an hour, your blood sugar drops dramatically. Why? Because the signal was sent, received, sent across the membrane, changes occurred, membrane proteins went in, sugar left the blood and went into the cells. So that's the pathways, that's the function of each of these. Now, oops. Let me record this again because it was so important what you just said. I had to turn the recording on again. Absolutely. Every receptor is specific to the signal. So that receptor that lets sugar into the cells only fits insulin. Insulin only fits in there. Nothing else fits. So that's how you make sure that you get the right thing happening when you need it to happen. Excellent question. Some really great questions here. So when we look at the lab that I want you to do, and again, we only have 15 minutes, but I think it was worth it. I'm sorry that so much nonsense ended up taking away from our time, but you're going to have instructions. Now here in this lab, you see that they draw on the same color here. But that's because they're not using this to distinguish between the hydrophobic and hydrophilic parts of your membrane. I want you to use this activity to prove to me that you understand that parts of this membrane are hydrophobic and other parts are hydrophilic. So I expect that you are going to be able to color the heads, the hydrophilic heads, one color. Do you see what I'm doing? Do you see how the side is one color? And I expect that and I should maybe do it. Try not to use a deep marker, but you know that all these should also be blue. And I'm just using blue. You can use whatever color you want. But that all the heads have to be one color because they're all hydrophilic. They all love water. In fact, in this protein, everything here loves water. So I'd expect that you are going to be able to show me this by color coding all this as being blue. All this is blue. Why? Because it's touching what? Water. Anything touching water should be all the same color. You can shade it different shades, but the bottom line is all this should be blue, correct? Yes. And there should be, so when you build these, please make sure you can show me that the stuff that's hydrophilic is all hydrophilic. The stuff that's hydrophobic should all be yellow. There should be no question. So all this should be yellow. All this should be yellow because it's in the membrane. Now this is a channel protein. So everything in the center here should be blue. That should be blue because it's all all has water in it. All this should be blue. Everything sticking out, everything sticking in. But the stuff that's in,
Wait, is that one of those gated channels right there?
this is a channel protein. But this stuff here, in this protein, this has to be yellow here along this edge because this edge is touching the lipid. And then it has to have the protein has to have a blue part because it has a part that's touching water. So it has a blue part and a yellow part. So you should be able to designate that for me. I'm gonna have to draw a black line because I think it's hard for you to see without there being a black line. You don't have to do this because yours is already drawn for you. But you see this protein, this part of the protein has to be blue, where this part of the protein has to be yellow. This part of the protein has to be blue, where this part of the protein has to be yellow, and of course all the way around. And this protein goes all the way around here, and this protein goes all the way around here. So this protein all has to be pretty significantly blue or hydrophilic in order to be able to sit in water, because like dissolves like. And the part that's embedded in the membrane has to be yellow because it's touching lipids. It's being dissolved by lipids, so it has to be nonpolar. So it's going to be true of all your drawings. Now, there are drawings here. They show you how to fold these things. Do you see that? Pay attention to that when you do it at home. You're obviously doing this at home. When you're done, you see this is getting taped, right? If you have trouble, you can come tomorrow morning at 8 o'clock in the morning, and I'll be here. I can help you build these during lunch or advisory. You can get a permission slip, come in here. Not permission slip, pass. Here is a protein you build. You cut it out, you close it up, and then you're going to stick it onto the side here. Here they have tape. You're going to stick it onto the side. So what color is this going to be that's touching this yellow part here? Yellow. Because this yellow part is hydrophobic. The part that's touching the blue section, which is this, oops. Yeah, that's right. This should all be blue because these are the phospholipid heads. All these are blue all the way across. So the part that touches this and any of this should be blue. There should be no question that this should all be blue because it is touching, it has to be hydrophilic. And the part that has to be hydrophobic has to be this yellow part. So this all has to be yellow because it's touching the hydrophobic part. So as you make these, so let me be clear. When you're looking at this and you're seeing this is a phospholipid. So it has a hydrophilic head, blue, correct? And a hydrophobic tail, two tails that are hydrophobic. 1, 2, connected by a glycerol molecule. Is that clear? So this is all hydrophobic here. So is this, all hydrophobic. They dissolve each other, no problem. But this blue one, these blues are heads, and these heads are hydrophilic. Is that good? So when you look at it, these are all the tops of the heads. These are all the bottoms. So all these have to be blue as well. Do you see that? These all have to be blue as well. And anything that's in the yellow has to be that same color. Anything that's out in water has to be hydrophilic. So in other words, you have to have a key that makes sure you understand, that makes it clear to me that you understand anything that's touching water is going to be one color, anything that's hydrophobic is going to be another color. And then when you look at these proteins, they show you what you're going to do. You're going to follow these instructions, and you're going to cut out the solid line, and you're going to fold on the dotted lines, and you're going to tape them. You're going to tape them closed, and you're going to shape them, and then you're going to place them. Many of your colleagues have already finished this, and they did it in like an hour on their own, or half an hour together. What I just say? Whatever you don't finish in class, you do on your own. This is due on Monday. The question was, what is this? What about the sides? Remember, you're taking just a chunk of the membrane that's a ball from a cell that's a ball. You're cutting a chunk, a little rectangle out of it, and you're building it here. That's what you're doing. So you have to imagine this is just a piece of a round sphere. Suggestion, obviously the first thing you do, what I would do before I started cutting, is I would color all the things that have to be hydrophilic. These are all hydrophilic. All this should be hydrophilic. See how I'm using, you could use a highlighter. Yours obviously is not colored. Yours is black and white. So you should be able to have a lot less trouble coloring it correctly. So all this should be one color. All this should be one color. All the lines here should be the same color. All the heads are all hydrophilic on all sides. This is also all hydrophilic. So is this. The only thing that should be yellow is this stuff here. Then once you have it colored correctly, and you're sure you have it colored correctly, then you're going to cut along the solid black lines. The dotted lines are for folding. Some of you are going to mess this up. Some of you are going to tell me you don't understand, and I'm literally watching you not pay attention. I'm going to list the things for the record, for your parents' sake, all the things I've seen happen today. Giggling, talking, communicating, trying to get chargers for their phones, getting up and getting the chargers for their phones, going underneath tables, sitting back down, all these little, I could list, the list goes on, of these 5 kids, that were not doing what they were supposed to be doing. You know you are. I'm just pointing that out. Just for future reference. So here we have you color all this blue, then you cut it along the solid black line, and you have the dotted black line that you're going to fold on. You're going to follow directions. The directions are there. They're clearly listed. You're going to build this membrane, and it's going to look something like this. It's going to be a 3-dimensional box made of paper, folded. It's going to be a 3-dimensional box made of paper and folded. It's going to have the yellow part and the blue part, or whatever colors you choose. It's going to have an internal yellow side, and it's going to have a different color for the hydrophilic side. And I'm just sketching it out here. And it's going to be 3-dimensional. And you're gonna fit the protein on it, and see what part touches the yellow, what part touches. Then you have these. Before you color them, cut them out along the solid black line. Then fold them along the dotted black lines. And then dry fit them. What do I mean by dry fit them? Fit them on the membrane. You already built the blue, and the part that touches the yellow, you're going to color it yellow. And the part that touches the blue, you're going to call it the parts that are hydrophobic, you're going to color code it hydrophobic. The parts that are hydrophilic, you're going to color code it hydrophilic. And you're going to make sure it matches and it makes sense. I'm going to quickly look at it. I'm going to know right away whether you got an A or an F. You have an A if the color codes are correctly matched. You're going to have an F if they don't match.
What did this do?
Obviously there'll be some subtleties.
What does it do?
It'll be due on Monday. Here's the handout. Nothing is due on Friday. Everything's due on Monday. Yeah, Friday you can't come in the morning. Put it on our table. Put it on our table. Put it on our table. No, you put that together. At this point, I'd like you to take and put your chairs up, and I'd like to see the 5 people. Don't make me call your name. I need to see the 5 people that were distracted up here. I need to see the 5 people that are distracted up here. I'm about to call your name. Destiny, come up here.
Oh man, I got. Oh man, this way. I have some distraction going back and forth.
I need to see the other people that were distracted up here as well. I'm about to call your names.